So what I'm going to talk about first is a little bit about the stormwater management regulations, SWPPPs, and the BMP Clearinghouse. We've talked a lot about erosion and sediment control this morning. We've talked a little bit about the different kinds of BSMP authorities. So what I'm really going to dive into now is the nitty-gritties of the SWM regs themselves. Some of you are going to be very familiar with this already. I apologize if you've already got these memorized. So it's going to cover some of the basics in terms of like the big numbers you got to watch out for, but hopefully for some of you who are a little more familiar with this material, I'm going to also give a little bit of background information. Hopefully some of that might be new and interesting for you. This is what we will discuss today. So first, we're actually going to go really quickly through the SWPPPs. I'm banking a little bit on everybody's familiarity with the SWPPPs, so we're not going to spend too much time on that. Then we are going to go through the two major portions of stormwater management, which is water quality and water quantity. We're going to have a little bit of a discussion on offsite compliance options, and then we'll talk about the BMP Clearinghouse. So SWPPPs. Stormwater pollution prevention plans. They're a pretty big deal, right? They've got a lot of different kinds of information that are inside of them. Why do we do them? We do them for what I think this picture captures beautifully, which is that we have clear water coming through one side of the tributary, and then we have polluted water, or I shouldn't say polluted. We have water that contains sediment coming down through a second tributary. This is the confluence where the two meet. Eventually, because it's in this area, it's all going to go down to the bay. So stormwater and stormwater pollution prevention plans, as part of the stormwater pollution prevention plan, is meant to prevent sediment from getting into the bay. And oftentimes the sediment itself is what's carrying those nutrients. The ones that we particularly care about are going to be nitrogen and phosphorus. Something I think is kind of fascinating is that, can you tell I'm a nerd because I find this fascinating? But so we used to have regulations that were specific to NTUs. Now, NTUs stands for, I can't remember the first word, it's like neophylatic or something, but it's turbidity. It's a turbidity unit. And it's a really fancy way of measuring how cloudy the water is. The way it's actually measured in a lab is you take your water sample and you shine a beam of light through it, and it's basically how much of the light you're shining through the water comes out on the other side. So if you've got pretty clear water, then you're going to have a low NTU number. If you've got pretty turbid water, you're going to have pretty high NTUs. We don't have to do NTUs anymore, good, but we have other things that are in place instead. This is literally verbatim the regulations language regarding stormwater pollution prevention plans. I'm not going to read this to you. That would be very boring, especially after we've all eaten. We're just going to fall asleep. So I'm just going to point out some of the things that are kind of the highlights. The pollution prevention plan, well, the stormwater pollution prevention plan is meant to control the stormwater volume and velocity. We're going to talk about those more when we get to the actual SWM regs themselves. It's meant to control your discharges, and while the construction is taking place, it's supposed to prevent the soil that has been exposed or disturbed from entering those waters and therefore leaving your site. Oh, it's this picture. This is our host. That's Dan on site. And as Jamie mentioned this morning, the frequency of the inspections has been changed as well. Okay, stormwater quality. Why do we care about stormwater quality? Well, for us particularly, everything that we have drains into the Chesapeake Bay. Chesapeake Bay has its own TMDL. That's a total maximum daily load. I'm going to talk about that a little bit more later. But the thing that we care about when it comes to water quality is that then we start having pollution problems. If we've got really high levels of nutrients in our water, once it gets to the bay, then we start having problems like algal blooms. A lot of times there's a little bit of misconception there. Well, algae is a plant, right? And if it's an algal bloom, that's good, right? That means we've got lots of plants in our water. Actually, no. So algal blooms do a lot of different kinds of things to the chemistry of the water, but one of the main things they do is remove oxygen from the water. For those of us who took a lot of chemistry, this was like called DO, dissolved oxygen, definitely gets reduced during algal blooms, or immediately after, excuse me. So the state of Virginia has implement these regulations. These are the 2014 regulations. This is not the old stuff. Jamie was talking about being grandfathered, time limits of applicability. This is the new stuff. This is the current stuff that became effective July 1st, 2014. So what we're going to focus on is the nutrient loading limit. Particularly what we care about is phosphorus, total phosphorus. There is a cap on how much total phosphorus can leave your site. For a new development, that's anything that's brand new, going in for the first time, your magic number is this guy right here, 0.41. 0.41 pounds of total phosphorus per acre of your disturbed area. Why 0.41? We're going to talk about that in a second. We have two different kinds of development that can happen, though, in our state. One is completely new development, taking an undisturbed area, and we're going to change it into something else. Usually, we put in new impervious cover as part of that. Or we can have redevelopment. So redevelopment is specifically defined in our state regs as prior developed land. And what that usually means is that there's already existing impervious cover in that site. So a good example would be there's an abandoned strip mall. There's a strip mall that hasn't been used for 20 years and it's in disrepair. A developer can come in and tear it down and put something new there, but it was already existing impervious cover, so that would be considered redevelopment. Now let's say they put in exactly the same footprint of impervious cover for that new strip mall. Then that would follow under the no net increase in impervious cover. So if it's a large site, and large in this case, the tipping point is 1 acre. If we've got a site that's disturbing more than 1 acre, but still has no new impervious cover, then you have to have an improvement of 20% from what it used to be. It can't just be, oh, it used to be this, I'm putting in the exact same thing. There's going to be no changes. You do actually have to have a little bit of improvement in terms of capturing your nutrients that are leaving your site. If it's a smaller site, it's only 10%. And again, the tipping point is 1 acre. Most of the time, particularly for redevelopment projects, we have a mix, right? We're going to have the new strip mall that's going in, but I'm also going to take down a couple trees and expand the parking lot, okay? In that case, we have net new impervious cover. And so those two are treated differently. Whatever is your net new impervious cover is subject to the new development cap of 0.41. But everything else that was basically in the footprint of your old impervious cover is subject to the 20 or 10% based on its size. Any questions? Okay, so why 0.41? This is really, really technical. So I'm just gonna kind of give broad strokes here. Using the VRM, which is the Virginia Runoff Reduction Method, that's how we actually calculate our loads and our loading limits for any projects in the state of Virginia, how we comply with our water quality regs. We had, there are several different kinds of land covers and hydrologic soil groups that go into the VRM. That's how we determine what our nutrient loads are. And the main thing is the soils underneath. Are they well draining or poor draining soils? That's what the HSG-ABCD stands for on that slide. Engineering talk. And then you have to consider your land cover. Does it have already impervious surface? Does it have trees, or is it just managed turf? And if it is managed turf, is that turf grass being fertilized? So looking at sort of a combination of different percentages of a mixture of those three land uses over a weighted average of the 4 different types of soil groups, we come up with these kinds of numbers. So if we consider about 10% impervious surface, we get a loading of 0.41. If we drop that all the way down to 5% impervious and consider the rest of that forested, we drop down to 0.30. Basically, this is math, just math. Here's a graph to make math look pretty. There was another study, however, that was looking at the the amount of land that has been converted historically, particularly in the state of Maryland. And you can see they had conservative, unconservative, and moderate estimates. So this is the extreme on one end, this is the extreme on the other end, and here's somewhere kind of wishy-washy in the middle. So based on those numbers, we get a forest load of about 0.11 and an agricultural load of about 0.74. Again, numbers, really what this all boils down to is this magic slide, which says 0.41 is a compromise. 0.41 is somewhere in the middle. And this was something that we could get a whole lot of people to generally agree with. For those of you who are engineers or interested in the Chesapeake Bay, they have the new Phase 6 model, watershed model is out, and it's on their website if you are interested in taking a look at that. So why the reductions for redevelopment? If we're going to meet our goals for protecting the Chesapeake Bay, not only do we have to, those are strong words, not only should we limit the loads that come from anything that's new, but we should make improvements whenever we can. If we're already going to dig up that broken, torn apart asphalt parking lot and put in something new and better, let's actually improve the loading at the same time. But the 10 and 20% reduction from a real small site can actually become kind of onerous. As we'll see later with the different BMP Clearinghouse options, it can be a little hard to achieve 20% reduction if you have a really small footprint. Oh, and here's what I mean by prior developed land. This is literally one of my projects. It used to be a parking lot. Okay, so what does this mean? What do these new 2014 regulations mean? So things that we used to be able to construct and develop, and the traditional method used to just be, let's put in a big old pond. Well, maybe you can still put in a pond, but it's probably going to have to now be part of a larger integrated plan to deal with all the stormwater management on your site. So we would go from traditionally just one extended detention pond that would satisfy your stormwater management reg needs based on the old regs. But now we're going to go into something that has multiple different kinds of BMPs. There might be treatment trains. They might flow from one into the other, and so on and so forth. So there's a little bit larger holistic picture whenever possible. Not always possible, but whenever possible. Okay, so that's what's in the water, water quality. The other thing we care about is how much water there is. So that's water quantity. Where, sorry, I'm distracted by the dog. Oftentimes you go far enough downstream from wherever your site or your project is located, and it's going to be most likely entering a stream. If there is a lot of water with a lot of power that's entering that stream, it can cause pretty severe stream degradation. This is one of our projects from 2005-ish. So this was in Reston, for example. And not only do you have problems with, I mean, it just looks ugly, right? But there are lots of other problems with this too. You've got exposed infrastructure. Sometimes that infrastructure can be sanitary lines. Nobody wants exposed sanitary lines. All of this exposed bed and bank material may be carrying nutrients, which again, in a storm event, is going to get entrenched in that water and shot all the way down to the bay. Not to mention, like, there's property loss here. You know, your homeowner right here is losing their backyard. Nobody's happy. So one thing that we can do is control how much water we let leave the site. There are three different ways that to simplify, there are three different ways that stormwater can leave your site. It can leave through a man-made system. That's going to be things like your curb and gutter, pipes, ditches, things that we're a little more familiar with, right? It can be a natural conveyance system, so that is going to be the stream or tributary that's adjacent to your site, or it can be a restored conveyance system. We're seeing more and more of these now, especially because some of us in the stream restoration business have implemented some projects over the years. So all three of those different systems have different regulations and different ways. They have different amounts of water they can safely handle. Let's say that. Don't read all of this. This is an old slide. So for natural conveyance systems, and this was, I think, one of the major contentions for the 2014 stormwater management regs, we implemented something called the energy balance method. The energy balance method is meant to be a mass balance equation. It's meant to mimic, essentially, forested conditions. So pre-development hydrology, roughly. I think this graph is much more explanatory than all the words. So if you look at the bluish purple line, hey, hydrology 101, this is your time discharge graph. And so the line itself is showing you the amount of discharge. That's going to be your peak flows. And anything that's underneath the graph is your total volume. Okay, with that in mind, your blue-purple line here is what we would call the pre-urbanization hydrograph. It starts raining in a certain spot. Yeah, you've got a little bit of that rain immediately leaving your site. You've also got a little bit of it starting to slowly meander through the shrubs and the trees, and eventually it leaves your site at a certain point with a certain peak, and then there's sort of a trailing arm. Once we start putting in a lot of impervious cover, once we start changing the conditions in that site, we get what's usually called a flashy system. So that's this red line here, the post-urbanization. That means as soon as it rains on the roof, it's in the pipe. And as soon as it's in the pipe, it's at the outfall. And so it's a lot of water in a really short amount of time. So the way we used to do stormwater management was we would just control the peak. We would try and get this hydrograph, this is the green one now I'm pointing to, the post-urbanization, we usually just cared about the peak. We just didn't want a whole lot of water leaving the site all at once. But if you look at it, it actually has significantly more volume, and it's still in a relatively short amount of time. So the idea behind the energy balance method was to reduce the peak even further than just pre-development conditions. So there's no doubt we're going to have more volume. That's just inevitable. We've taken down a tree and put in a parking lot. We're going to have more volume, less infiltration. But let's spread that volume out over a significantly longer time and bring down the peak as much as possible. Still awake? Okay. Here's kind of the big takeaway equation for the energy balance method. It is based on the 1 year, 24-hour design storm. So under the old regs, everything used to be the 2 year and 10 year was what we were focused on. So this is a little bit different. It's the 1 year. And it's a little less obvious when it's written long form like this, but it's meant to be like a ratio, right? Whatever we had before, we're trying to match it, weigh it equally in post-development condition. And we have the improvement factor, again, based on your site size. 1 acre, again, is your tipping point. So it's either an improvement factor of 0.9, that would be essentially your 10% improvement. Or if you're above an acre, it's 0.8, that's your 20% improvement. So you can sort of see the parallels there. What if you're discharging to something other than a stream? If you're discharging to a pipe, for example, or a restored conveyance system. So the man-made pipe, we actually go back to the 2-year analysis. The man-made systems is we have to have 2-year non-erodible velocities. So erosion inside of a pipe, especially a reinforced concrete pipe, not terribly likely. But remember, there are other kinds of man-made systems. They can be ditches, they can be grass-lined or earthen ditches. And so that's where we have to start really making sure that the velocities are not going to just rip up those man-made systems. For a restored conveyance system, that's something that somebody else has already designed and implemented. Basically, you just have to go back to those designs and say, well, the increase from my site can be managed comfortably by the design of this site that's already in place. That can be hard to prove, and it also can sometimes be hard to find the original designs. If you cannot meet either of those for any reason, or if it's just a complete unknown, big question mark, you can always use the energy balance method to satisfy your channel quantity protection requirements for any kind of conveyance system. That's why they're listed here, but they also all have arrows to the big white box saying, or you can do this. So something else that's interesting about quantity is we don't care, we care how much is leaving our site, but we also care about what's happening downstream. So not only do we have to understand how much water is leaving our project area, but we have to also figure out how much water is happening at what we call the limits of analysis. And the limits of analysis is a place way far downstream. Keep using lingo, it's the 1% rule, meaning if my drainage area is 1 acre, I have to go somewhere downstream that's of my site, that my site drains to, that has a drainage area of 100 acres, okay? And then you have to analyze at that point, what are the changes in your water quantity. So the energy balance and the 2-year non-erodible velocities, those are for your channel protection. We also have to worry about flood protection. So flood protection is split into two categories. This is no longer the natural conveyance system or the man-made system. Now we just have to look at that point, the limits of analysis, and say, in a 10-year, 24-hour design storm, does that spot currently flood? If it does, and if you can prove it does, let me say that again, if you can prove it does, it floods at that 10-year, or at that limits of analysis, then what you have to show is for that 10-year storm, your project site is not increasing any of the flows. So my site is basically contributing a negligible amount for the 10-year, 24-hour design storm, okay? If it does not experience local flooding, or you don't know, or it does and you can't prove it, then you have to demonstrate that there's adequate capacity. So that's just basically saying that at that point, 100 times downstream, the limits of analysis, whatever is there as the conveyance system is able to handle the entire 10-year storm. If it's a pipe, that means, you know, if it's a 48-inch pipe, that means in the 10-year storm, that pipe is only 12 inches deep. If it's a stream and you have a cross-section of that stream, you can prove that the 10-year storm is within the bed and banks and it's not overloading. That gets a little tricky for some of us in the stream restoration business because we actually want it to go past the bed and banks even earlier than the 10-year storm. But that's another thing to talk about. Okay, so what does this mean? For developers, there's a couple of things. It is written into the stormwater quantity regs that if you satisfy the stormwater quantity regs, you don't need to consider adequate outfall. There are some major caveats to that. Localities can require it. And also, if you read it really carefully, the minimum standards kick in at 10,000 square feet of disturbance, whereas the stormwater regs outside of the Chesapeake Bay kick in at an acre. So if you've got a site that's between 10,000 and an acre, you're kind of in this weird area of, what do I do? On the other hand, if you're inside the Chesapeake Bay area, then it's 2,500 square feet. I'm nodding. Yes, everybody in this room knows that. Okay, so let's say you're a developer or you're working for a developer and they want to build their site, residential, commercial, industrial, whatever it's going to be, and they just want to keep using ponds. I've used ponds for 30 years. That's all I want to do. Well, okay, we can make that work. The footprints of your ponds are typically going to stay about the same because it's based on the 10-year storm. It's got to be able to handle the 10-year storm, and that's the same as it was in the pre-2014 regs. The difference is that pre-2014, the control structure of the pond had a BMP orifice for the 2-year storm. It's now going to have a BMP orifice for the 1-year storm. That's a little bit different. But, you know, can be done. So let's say you're working on a site and there's just no way to meet your quality requirements on site. There are certain circumstances where you can buy credits. Jamie was talking about this morning as well. So what is written into the regs as to the situations for which you can purchase credits is that at least you're trying, right? So you've got at least 75% that's being treated on site. Your entire disturbed area is less than 5 acres, or not and, or your load requirements are less than 10 pounds, okay? So you don't have to meet all 3 of those criteria, you only need to meet 1. However, you still got to get your approval from your VSMP authority. The non-point nutrient offset program is managed by DEQ. There are banks listed on DEQ's website that there's a listing of which banks have been approved, which hydrologic unit codes they serve, and roughly how many credits they have left. So if you're working on a project and you know you're going to need to purchase credits, that's a really good place to start looking to get your availability letter. Jamie was saying is needed for your permit. So a little bit about stormwater management and how it relates to things like the TMDLs and impaired waters. And I'm talking super fast, so please slow me down and ask questions if needed. In the language of the regs, it's actually saying very clearly, if your project is in an area that is an impaired watershed, has a waste load allocation limit, that's what the WLA stands for, alphabet soup, then you actually have to meet those requirements, whatever they may be. A little bit different when it comes to the Ches Bay. So for the Bay, if you are meeting your stormwater management state regulations, it is kind of implied that you are already meeting the Chesapeake Bay TMDL requirements. This is kind of a handier thing for those of us with smaller projects. But as always, you do need to double check, because it could be, there are lots of different kinds of TMDLs, lots of different kinds of impaired waters, and some of them overlap. Some of them have more than one pollutant that they're regulating. It could be sediment. It could also be PCBs, like Jamie talked about this morning. Some of them are for things like temperature. So just be sure that you actually check it. And again, it is on the DEQ website. that is a whole lot of boring technical information in a short amount of time. Okay, I'm gonna just keep going. I've lost a couple of you to sleep, but that's okay. So those are the regulations that we have to meet. So how do we do it? How are we going to comply with those regulations? Well, that's where the BMP Clearinghouse comes in. BMP stands for Best Management Practice, and these are meant to be our stormwater management facility, the practices, controls, and measures that we put in to manage our stormwater. It's specifically listed in the regs that you can go to the BMP Clearinghouse. It's labeled as Virginia Stormwater BMP Clearinghouse website, which is good that it's kind of vague language because that website changed. It used to be acronyms. WVRTTC, but it's something different now. Well, it's still that, but it's the second part of the website. So this is what the website looks like now. It used to be a little different, but this is, I think, really clear and straightforward. You have 4 drop-down menus from this main page. The first one is just background information. I've given you a lot of that background information just now in super fast mode. Jamie was mentioning that there are the 2011 specifications, and then there are also 2013 draft specifications. Both of those are available on this website. And then the manufactured treatment devices. If you're going to use one of those on your site, it has to be DEQ approved. It will be on this website and listed, and each of those separate proprietary devices has different efficacies of how much water they're actually treating. So you'll have to put that into your calculator to see if it's enough. If you need it. So these screenshots, by the way, are going to be from the 2011 BMP Clearinghouse, just as an FYI for any of you who might look at these every day, such as myself. But there are 15 sort of quote-unquote basic strategies or basic BMPs that can be used for your stormwater management needs. Some of them have multiple levels of design, so either a level 1 or a level 2. The level 2 is usually going to provide more treatment, but that's going to mean things like it might be deeper, like if it's fire retention, it might be deeper, have more storage, something along those lines. Just taking a look at this graph, or excuse me, this table, what I'm really going to point out to you is this last column in yellow. This is our total phosphorus load removal that is potentially available from your BMP. Taking a look at this column, hopefully your eyes are going to the big numbers. These are like the big bang for your buck, right? So it's going to be things like infiltration practices, fire retention practices. Both of those, the level 2 designs, have really high numbers. And then, of course, your rainwater harvesting can be up to 90%. Of rainwater harvesting, I'll show you a picture in a second. It's basically just a big barrel, and then it kind of becomes a settling tank. So that's how it works in terms of removals. We're going to go through these one at a time, but I'm not going to read everything that's on these slides. If you want more information on the BMP Clearinghouse, I strongly recommend that you download it from the website, read through it. I'm pleased that Jamie mentioned the committee, because I actually get those emails too about the committee and about things that need to be improved. So first one, impervious surface disconnection. Very often we have a pipe that leads to another pipe that leads to another pipe, right? And they're all connected and water just shoots all the way through. It's super fast. Well, if you can just interrupt it at one point there, you can significantly reduce how much water is leaving your site. Really good example is the drain from your roof on your house. A lot of times that the gutter drain goes right into the city stormwater pipe system. If you can have it instead go out on your lawn, then you're going to reduce how much water is ending up finally in the pipe system. You can also improve your treatment of that interrupted water in various ways. Maybe have it flow over some gravel. That's going to slow it down a little bit. You can throw in some compost there. Maybe it'll soak up and get a little bit more treatment that way. This is your available treatment removals from impervious surface disconnection. Again, it depends on what your native soils are. What we call A and B soils are, they don't drain well. They're poorly draining soils, so it's going to be a lot of like clay materials. It's actually pretty prevalent. Wait, I'm doing that backwards, aren't I? Yes. Sorry. The C and D soils are the poorly draining soils. It's like doing math in front of people. You just like can't think. The C and D soils are the poorly draining soils, and then the A and B soils are going to be things that have more sand content, and they're going to be well draining soils. So that's why you get more removal from the A and B soils than you would the C and D, because the removal is actually the water from your downspout is actually soaking into the ground. And if it's a well-draining soil, it can soak up a lot more, which is why your removal is better. Sheet flow. So sheet flow can be naturally occurring if you've got a really large flat area. This is water that is flowing in a really short, shallow depth, like really shallow depth of like less than half an inch, and over a wide area. And it can flow as a sheet for a little while, but naturally water wants to kind of come together and become what we call concentrated. So it's only going to have a short length. And that'll be on the next slide, actually. But if you can get it to sheet over something that's vegetated, such as grass, then the grass is actually able to pick up a lot of the particles that would be inside that water. And so you can get some treatment just by making it sheet flow over the grass. Again, matters what your soils are. You can, in this instance, if you are intentionally sending it to sheet flow over, say, a grass area, you can mix compost into that soil, and it will give you a higher improvement rate. That's what the CA stands for, is confidence. And then you'll see over here we have a little bit of language on how long we consider it sheet flow. If you're using an engineered level spreader, which I know this doesn't have it, nope. Shoot, I've got a really great picture of an engineered level spreader. But those have to be pretty long, the minimum of 13 feet. Or if you've got something else, say your natural site conditions are sheet flow, if you can just prove that you're going to maintain that. You can, again, it's locality specific, but most of them are around 100 feet for your flow, maximum flow length of sheet flow. Grass channels. Grass channels are exactly what you think it is. It is a trapezoidal channel lined with grass, and it is a conveyance system. This can be really good for linear areas like along parking lots, and this one happens to be along a sidewalk, a walking trail. And if you can hold a certain amount of water in here, then that's how you start to get your treatment as well. A little later on, we're going to talk about something called a dry swale, and there is a difference between a grass channel and a dry swale. Just planting the seed of that. Grass channels, like a lot of the other practices, if you can mix in a compost amendment into your soil, you can get more treatment. Again, why does the compost amendment create more treatment? It's because it's basically fluffing up that soil, making it have more gaps, and it's going to capture more water. So number 4 is the compost amendment itself. It is very rare to just have Compost Amendment as your BMP. That would be basically like removing all of your topsoil and just putting in compost. Nobody's really going to do that. So instead, this is more something that we would use in addition to something else, or it would become a supplement and an additional part of some other kind of BMP, particularly anything that's having to go over soil. Number 5, the green roof. Green roofs are, well, we'll see one after this presentation. The green roof, it's kind of a no-brainer, right? Like one of the biggest impervious surfaces that we have in development is the roof. We don't want water coming through our roof, so of course we make it waterproof. But it's also a large area at the top of our structure that isn't infiltrating any water. So let's get some of it before it leaves if we can. If you can convert your impervious roof into a water absorbing surface, then you can capture quite a lot of rain depending on the media that you use. There are 2 kinds of green roofs. You have the extensive and the intensive. That has to do with the soil depth. And usually soil depth is going to be dictated by things like your structural loading, how much that roof can hold, and what kind of plants you want to put in there. If you want to put in trees, you're going intensive. Normally, we use really shallow rooted plants like sedum on green roofs so that the extensive is an option. Rainwater harvesting. So as I said a second ago, putting in a barrel and just getting all that water, sticking it in a big tank, it basically becomes its own settling tank. So all that captured soil, all those particles are just going to eventually sink down to the bottom. And that's part of the reason that you can get a huge amount of treatment out of a cistern or a rain barrel. We're going to take a look at one during our tour. It's actually this one. Rainwater harvesting has an additional design component to it that you have to consider. The VRM spreadsheet has really good, you just like plug and play basically in the VRM spreadsheet to figure out your treatment. But for rainwater harvesting, there's actually a whole other spreadsheet that you have to use. That's just an FYI. So you have to think about how much rain, how big is my tank, stuff like that. You gotta give it a little more consideration. Permeable pavement. This to me is the other no-brainer besides the roof. What do we have a lot of that's impervious? Roadways, things that we drive on. So in certain circumstances, depending on the kind of vehicle loading or the vehicle frequency, the kind of traffic we're looking at, it may be possible to replace that impervious surface with a pervious option. And there are lots of pervious pavement options these days. This is a huge booming field. And depending on what kind of pervious pavement you put in, you can get different levels of treatment and really wide ranges of cost. We'll do that later. I'm actually going to do this in front of you and pour water on our pavement. Another option, infiltration practice. So infiltration, this is kind of the best. If we could, this is what we would always do, right? We would capture the water and just let it sink back into the ground. That's ideal. That's also part of the reason that infiltration practices, if you can implement them well and correctly, you can get a ton of treatment. This is actually the highest rated treatment option, is infiltration. It is tricky though. And part of the reason it's tricky is because you have to be able to prove that your in situ soils, the soils that are there already, have an infiltration rate of at least ½ inch per hour. Yeah, I almost said day and then I second guessed myself. So that is really fast, basically sand, and we're never going to encounter that, particularly in some kind of development where we're going to have to compact a bunch of soil anyways, right? Just to get the heavy traffic and heavy trucks moving in. However, if you have this great draining soil on your site, maybe you can protect it during construction, and then it can become part of your infiltration practice. Bioretention. Bioretention is kind of a big umbrella word. It encompasses a lot of different kinds of practices, but it's a way of getting your water. Yeah, we can't get it all the way into the ground, but we're going to give it sort of fake soil and have it percolate through that fake soil as much as we can. Again, depending on how deep your soil is and how much rainwater it's getting, you can get a lot of treatment out of a level 2 bioretention facility. They can also become amenities. These can be really pretty, you know, pretty planting area out front, as long as somebody maintains it, right? Here are your specifications. Again, level 2 design, look at that, you can get all the way up to 90%. So you can have a pretty big project, but if you've got a way to convey all your rainwater to one big rain garden, you can get a lot of treatment out of that. There are, as I mentioned, different kinds of bioretention facilities. One that we're seeing more and more frequently is this urban bioretention. Urban bioretention just means that it's kind of small, it's in a limited area, it's usually got impervious stuff around it, like concrete for either the sidewalk or the building, and it's going to have things like liners. So there's a little bit more in terms of design, but again, get a nice little green spot in front of your building. Dry swales. I'd mentioned we were going to talk about this. So dry swales are, again, basically the trapezoidal channel, but it's grass lined. And the reason it's different from a grass channel is that we're actually going to put bioretention soil media under the bottom of it. So again, this is an instance where we're taking out the in situ soil and we're putting in something that drains better. And again, just like grass channels, really good situations for dry swales are going to be things like along the edge of a parking lot, along the edges of sidewalks, things like that. Wet swales. Wet swales are exactly what they sound like. It's basically a dry swale that has a little bit of water in it all the time. Again, there's bioretention soil media underneath. This is usually used in like really flat areas where you don't have a really steep longitudinal slope, so it's just going to sit there for a long time. And in areas that are like the coastal plains with high water tables, where you're not going to get a lot of infiltration of that water, it's mostly probably just going to sit there and real slowly move its way downstream. They often become very heavily vegetated. Filtration practices. This is a little bit different than what we were talking about earlier with the manufactured treatment devices. Manufactured treatment devices are, you know, you call up, I'm not going to say a brand name, but you call up a person with a brand name, you buy their product, and you put it underneath your catch basin. And it does the work for you. So you would actually have to design this yourself, but it's basically the same thing. It's usually an area where all of your stormwater comes together. Great places for these are parking lots, again, because you can just put in some curb cuts. All of your water is sheet flowing, goes through the curb cut, and then can go into your filtration practice. Things to think about with your filtration practice. You have to have an area that allows for the settling of your sediment in your rainwater, but also what are you going to do in those really, really big storms where you need to get rid of the water fast? So you do have to think about your overflow options, especially in something like this. Constructed wetlands. They are exactly what they sound like. I'm not going to spend a lot of time talking about that. It's something that Wetland Studies has dabbled in a lot. Okay, Then 14 and 15 are going back to sort of the quote unquote traditional methods. So this is going back to the wet ponds and the extended detention ponds. Again, a wet pond, what is it? All of our water is coming to one place. It's going to stay in this one place. It's a giant settling tank, and we've got some fancy outlet structure that's going to skim water off the top of it. That means the water off the top of it doesn't have as much sediment in it because the sediment's sinking to the bottom. So we're going to skim off the top layer of the water, and then it enters our pipe system. And then, of course, the extended detention pond. So the extended detention pond is similar, but it also is going to have some structures within it. And by structures, I mean you're going to do some interesting grading so that it's got like little, little mini ponds before you get to the big thing. How's that for layman's terms? Okay, and again, I flew through that really, really quickly. All right, let's go see some stuff.